Where is the p block in the periodic table? We are referring to columns 13 through 18 on the right-hand side of the table. Elements in the p block have their outermost or valence electrons in a p orbital. As you recall, there are 3 p orbitals in a p sublevel, and each orbital can hold a maximum of 2 electrons. This is why there are 6 columns in the p block. There is a simple relationship between the group number, the number of valence electrons, and the electron configuration. Group 13 has 3 valence electrons, and the electron configuration ends as ns2 np1. As we move across each column to the right, the columns or groups each gain an additional valence electron. The exception, of course, is helium, which has only 2 electrons. Within each of the 6 different families of the p block, there are significant variations in properties. Although all the members of the same family have the same number of valence electrons, their inner cores are different. The variations in the arrangement of the core electrons affect the physical properties, such as atomic and ionic radii, and ionization energies, as well as the chemical properties of the elements in the same family. For p block elements, the maximum oxidation state is equal to the total number of valence electrons. So, as we move from group 13 to group 18, the maximum oxidation state rises from +3 to +8. This is sometimes called the group oxidation state. For the boron, carbon, and nitrogen families, this is the most stable oxidation state for the lighter elements in each group. However, other oxidation states are possible for each group. Often, an oxidation number 2 away from the total number of valence electrons is stable. The stability of oxidation states that are 2 less than the group oxidation state are sometimes attributed to the inert pair effect. As elements get heavier down a column, the oxidation state 2 less than the group oxidation state becomes more stable. This does vary somewhat from group to group. Metalloids and non-metals are found only in the p block of the periodic table. Down a column, the non-metal character of the elements decreases. The heaviest element in each column has the most metallic character of that family of elements. There is a lot of diversity in the properties of p block elements. Since a given family may have metals, metalloids, and non-metals. Metals and non-metals have distinctly different properties. When comparing metals and non-metals, non-metals typically have higher ionization energies than metals. The electronegativities of non-metals are generally higher than that of metals. Therefore, metals readily lose electrons, forming cations. Non-metals typically gain electrons, forming anions. Compounds formed between a metal and a non-metal are essentially ionic in nature. This is due to the large electronegativity difference between the elements. The metal transfers an electron to the non-metal, and the oppositely charged ions that result are strongly attracted to each other. Compounds between 2 non-metals tend to be primarily covalent in character. The small differences in electronegativity result in a sharing of electrons. Oxides of non-metals are either acidic or neutral in nature. Acidic oxides, such as nitrogen dioxide, will form acids when dissolved in water. metal oxides are usually basic. For example, when magnesium oxide is dissolved in water, hydroxide ions will form. Let's focus our attention on the group 13 elements. The members of the boron family include boron, aluminium, gallium, indium, and thallium. The elements in group 13 exhibit a wide variety of properties. For example, boron trioxide is an acidic oxide. Aluminium oxide and gallium oxide are amphoteric. They can act as both acids and bases. The oxides of indium and thallium are basic. The first member of each family in the p block, that would be boron, carbon, nitrogen, oxygen, fluorine, and helium, have the smallest atomic radius in their respective families. Each of these exhibits some anomalous behavior as a result. For example, the elements in period 2 have a maximum covalence of 4. They never exceed 8 electrons because they can only use their 2s and 2p orbitals in bonding. For example, boron can form the complex ion Bf4-. The elements in period 3 and below can achieve expanded octets. Since these elements have unused d orbitals, they can have more than 8 electrons. Therefore, we observe the hexafluoroaluminate ion. We often observe that the first member in each group in the p block can form multiple bonds to itself and other elements in period 2. For example, carbon can form multiple bonds with itself as well as with nitrogen. These multiple bonds involve sideways overlapping or pi bonding of p orbitals. P block elements in period 3 and below can use d orbitals to create pi bonds. As a result, the elements in period 3 and below can achieve a higher coordination number than the first element in the group. The elements in group 13 will be the focus for the rest of this module. Boron is a fairly rare element. Less than 0.0001% of the Earth's crust by mass. This typical non-metallic element is found as a hard, black solid in its pure form. A photograph of boron powder is shown here. In addition to boron powder, boron occurs in several other allotropes, including crystalline boron and alpha boron. Only 2 isotopes of boron are found in nature. Almost 19% of boron atoms are found as boron-10, with 5 protons and 5 neutrons. Boron-11, which has 5 protons and 6 neutrons, is the most abundant isotope. In nature, boron is most frequently found in 3 compounds: orthoboric acid, kernite, and borax. In India, borax is found in the Puga Valley in Ladakh and the Sambar Lake region of Rajasthan. Aluminium is a metal, although it has many chemical similarities with boron. It is the third most abundant element and the most abundant metal in the Earth's crust, contributing 8.3% by mass. Important minerals of aluminium include bauxite, cryolite, and mica. the electron configurations of the group 13 elements all end as ns2, np1. For example, consider the electron configurations of boron and aluminium in noble gas notation. They both have 3 valence electrons. However, if we look at the electron configurations of the rest of the family, we see quickly that they are all more complex than for the s-block elements. This complexity affects the chemistry of this group. While boron and aluminium have core configurations identical to the nearest noble gases, as we saw just now, gallium and indium have 10d electrons in addition to the noble gas core. Thallium has 14f electrons plus 10d electrons in addition to the noble gas core. In general, atomic radius increases down a column. However, this trend is not uniform. Try to answer this question before continuing. Why does gallium have a smaller radius than aluminium? Answer: gallium has 10d electrons in addition to the noble gas core. These d electrons provide very little shielding from the nuclear charge, since d orbitals have little electron density near the nucleus. Thus, the outermost electrons in gallium are held more tightly than in aluminium. In general, ionization energies are expected to decrease down a column. For the group 13 elements, however, the expected smooth decrease is not observed, as shown in the table. This is due to the poor shielding by d and f electrons. As additional electrons are removed, the ionization energies for each removal increase. For example, the first 3 ionization energies of group 13 elements are shown. It should be noted that the sum of the first 3 ionization energies for boron is significantly higher than for the other group 13 elements. In general, electronegativities are expected to decrease down a column. For the group 13 elements, electronegativity decreases from boron to aluminium, then increases slightly down the column. This correlates with the deviations in atomic size observed in this group. The density of the group 13 elements increases down the family. Boron has a high melting point, 2453 Kelvin, due to its strong crystal lattice. The other members of the family are soft metals, with low melting points. The melting point of gallium is only 303 Kelvin, low enough to melt in the palm of your hand. Gallium's boiling point is very high, 2676 Kelvin, making it very useful for measuring high temperatures. Let's turn our attention to the chemical properties of the elements in group 13. With its small size and the high sum of its first 3 ionization energies, boron forms only covalent compounds. The formation of a +3 ion is unfavorable. The other members of the family, which are all metals, form +3 cations. Down the column, +1 ions become more stable. This is due to the outermost s electrons being held more tightly, and so only the electron in the outermost p orbital is lost. With 3 valence electrons, boron often forms compounds such as boron trifluoride, with only 6 electrons around the central boron. Such molecules are described as being electron deficient. They tend to gain 2 electrons to achieve a stable octet. Therefore, BF3 acts as a Lewis acid, that is, an electron pair acceptor. Try to answer these questions on your own before checking the answer. What is the hybridization of the central atom in BF3? Shown on the left. And for BF4 minus the product in this reaction. What is the geometry for each of these species? BF3 with a coordination number of 3 around the central atom displays sp2 hybridization. Its geometry is trigonal planar. In BF4 minus, there is a coordination number of 4 around the central atom. So, the hybridization is sp3. The geometry is tetrahedral. Aluminium chloride dimerizes to achieve stability. The dimer has tetrahedral geometry around the aluminiums. Trivalent compounds hydrolyze in water to form complex ions. Trichlorides in water form complex ions with 4 hydroxides around the central metal. In these ions, the metal exhibits tetrahedral geometry and sp3 hybridization. When aluminium chloride is placed in acidified water, complex ions form in which 6 water molecules surround the aluminium. These complex ions have an octahedral geometry. The aluminium is sp3d2 hybridized in these complex ions. Crystalline boron is unreactive towards air. Aluminium forms a thin oxide layer on its surface, so no further reaction with air will be observed, although aluminium is a fairly reactive metal. The group 13 elements form oxides when heated in air. For example, the reaction of amorphous boron and oxygen is shown here. When heated in nitrogen, the group 13 elements form nitrides. The synthesis of aluminium nitride is given here. Boron does not react with acids or bases. Aluminium is amphoteric. It dissolves in mineral acids, such as HCl, and it dissolves in aqueous alkali solutions. Aluminium reacts with dilute hydrochloric acid in a single replacement reaction, as shown here. Hydrogen gas bubbles out of the mixture. In the presence of concentrated nitric acid, aluminium forms a protective oxide layer on its outer surface, preventing further reaction. In the presence of hydroxides, aluminium reacts to form complex ions and release hydrogen gas. The group 13 elements, with the exception of thallium, react vigorously with the halogens to form halides. The reaction of aluminium with bromine is shown here. Try to answer this question on your own before going on. Why does aluminium form the octahedral complex ion A1F6-3, but boron doesn't form the BF6-3 ion? Answer: aluminium, in period 3, can use its unused 3d orbitals to achieve an expanded octet. Boron doesn't have any d orbitals, so it cannot expand its octet. Some important compounds of boron are borax, orthoboric acid and diborane. We will discuss each of them in turn. Borax is the most important boron compound. Borax is used as a flux in soldering and as a cleaning agent in leather industry and laundry. Found as a white crystalline solid, as shown in the photograph, borax is a decahydrate of sodium tetraborate that you see here. Borax actually contains the hydroxyborate ion tetranuclear units, illustrated here. Hence, the correct formula for borax is Na2B4O5 OH taken 4 times, 8H2O. Borax dissolves in water and the resulting solution is alkaline. As shown in the reaction, when borax is placed in water, sodium hydroxide is produced. When borax is heated, it loses its water off crystallization and swells. The resulting white, opaque mass is anhydrous sodium tetraborate. When the anhydrous sodium tetraborate is further heated, it becomes a transparent liquid. When solidified, this is referred to as borax bead, which contains sodium metaborate NaBO2 and boric anhydride B2O3. The borax bead test is a qualitative way to test for the presence of transition metal ions. A platinum loop is used to heat a small sample of borax in a Bunsen burner flame until a borax bead forms. The bead is then dipped into a small sample of the substance being tested. Then, it is held in the lower part of the flame, allowed to cool, and then heated in the upper or oxidizing part of the flame. The formation of a colored metaborates of transition metals identifies the presence of transition metal ions. For example, cobalt ions give a blue-colored bead in this test. Orthoboric acid is another important compound of boron. Its chemical formula is H3BO3. It is also a white, crystalline solid. Orthoboric acid is only sparingly soluble in cool water, but highly soluble in hot water. Orthoboric acid forms a layered structure. The molecules of orthoboric acid, which can be written as BOH, taken thrice, arrange in a plane, and the molecules link together by hydrogen bonds. Try to answer this question independently before proceeding. Why is orthoboric acid a weak acid? Answer. One definition of an acid is its ability to release hydrogen ions. Orthoboric acid is not a protonic acid and doesn't release hydrogen ions on its own. It acts as a weak loose acid. As shown in the reaction, it can accept an electron pair from water to complete its own octet, thereby releasing the hydronium ion. Since it is a weak acid, the Ka value of orthoboric acid is very low, of the order of 10 to the power minus 10. There are mainly two ways to prepare orthoboric acid. One way is to acidify an aqueous solution of borax. The balanced equation is given here. Another way to prepare orthoboric acid is the hydrolysis of boron compounds. For example, the reaction of boron trifluoride with water yields fluoroboric acid, HbF4, along with orthoboric acid. When heated above 370 Kelvin, orthoboric acid decomposes to form metaboric acid, HbO2. If metaboric acid is heated further, it will form boric oxide, B2O3. Diborane, B2H6, whose structure is illustrated here, is another important compound of boron. Boranes are a class of compounds containing only boron and hydrogen. Diborane is a colorless, highly toxic and extremely reactive. This colorless and highly toxic gas has a boiling point of 180 Kelvin. There are several ways to prepare diborane. One route involves reacting boron trifluoride with lithium aluminium hydride in presence of diethyl ether, as shown by this chemical equation. In the laboratory, oxidization of sodium borohydride with iodine produces diborane. Sodium iodide and hydrogen gas are the byproducts of this reaction. Try to answer this question on your own before continuing. Identify the oxidizing agent and the reducing agent in the reaction of sodium borohydride with iodine. Recall that an oxidizing agent is a substance that gets reduced. I2, which has an oxidation state of 0, forms an iodide ion with an oxidation number of -1. Since iodine is reduced, it must be the oxidizing agent. Therefore, NaBH4 must be the reducing agent. The third method for preparing diborane on an industrial scale involves the reaction of boron trifluoride with sodium hydride at 450 Kelvin. Sodium fluoride is the other product of the reaction. In air, diborane catches fire spontaneously. The reaction of diborane and oxygen is extremely exothermic, releasing 1976 kilojoules of energy for each mole of diborane. Boranes were once considered for use as solid fuels for rockets because of their exothermic reaction with oxygen. When placed in water, diborane undergoes hydrolysis to form orthoboric acid, as shown in the reaction here. Hydrogen gas is also released in this reaction. Diborane undergoes cleavage reactions with Lewis bases. In these reactions, the diborane molecule breaks apart to form borane adducts with the Lewis base. Two examples of these cleavage reactions are shown. One with trimethylamine and the other with carbon monoxide. Diborane can react with ammonia. Initially, the reaction of diborane with ammonia produces an adduct diammoniate of diborane. This exists in a slightly different form, as shown in the chemical equation. When this substance is heated further, borazine, B3N3H6, is formed. Note the alternating boron and nitrogen atoms in the 6-membered ring of borazine. Since it resembles structurally with benzene, it is called as inorganic benzene. Diborane is an electron-deficient molecule. Notice the peculiar structure of it. The 2 boron atoms and the 4 terminal hydrogen atoms of the molecule are all in the same plane. These 4 terminal BH bonds are regular 2-centered 2-electron bonds. The bridging hydrogen atoms lie above and below this plane. The 2 bridge BHB bonds are unusual 3-centered 2-electron bonds. The bond lengths are different as well. The bond length of the bridging hydrogen and boron is 134 picometers in length, while the bond length of the terminal hydrogens and boron is only 119 picometers. The boron atoms in diborane undergo sp3 hybridization. The overlapping of a vacant sp3 hybrid orbital of one boron atom and sp3 hybrid orbital of another boron atom containing one electron with the pure s orbital of bridging hydrogens containing one electron results in the banana bonds. Similarly, other banana bond is formed on other side. Thus, the 2 banana bonds formed lie above and below the plane of the boron atoms. The remaining 2 sp3 hybrid orbitals of each boron atom overlap with terminal hydrogen atoms to form normal sigma bonds. This results in the formation of 4 terminal hydrogen bonds. Boron forms a series of hybridoborates. One such ion is the borohydride ion, BH4-, which has a tetrahedral geometry. Sodium borohydride and lithium borohydride can be prepared by reacting the metal hydride with diborane, as shown in the equation here. Borohydrides are good reducing agents. Thus, they are widely used in organic synthesis, as well as to prepare other metal borohydrides. Boron has a number of applications. Because it is a hard solid with a high melting point, low density, and low electrical conductivity. Boron fibers are used to make bulletproof vests and light-weighted composite material for aeroplanes. The boron-10 isotope has a high ability to absorb neutrons. Therefore, metal borides are used as control rods and protective shields in nuclear power plants. Borax and boric acid are used in the manufacture of heat-resistant glass, such as Pyrex. They are also used to make glass wool and fiberglass. Borax is used as a flux for soldering metals, for heat, scratch, and stain-resistant glazed coatings for ceramics, and in the manufacture of medicinal soaps. Dilute aqueous solutions of boric acid can be used as mild antiseptics as well as an eye wash. Let's turn our attention to the properties of aluminium. Aluminium is a bright silvery white metal. It has a high tensile strength. It also has high thermal and electrical conductivity. In fact, its electrical conductivity is twice that of copper when compared on mass to mass basis. Aluminium forms a number of alloys with various elements, including copper, manganese, magnesium, silicon, and zinc. Aluminium and its alloys are readily shaped into pipes, tubing, rods, wires, or foils. Hence, aluminium and its alloys are widely used in packing, cookware, utensil making, construction, aeroplanes, and transportation industry. Recycling of aluminium is significantly less expensive than mining and refining aluminium ore. It's better for the environment too. So always recycle your aluminium cans.